Yeah, right. So I need to put that on. So how is my voice? Is it going out clear? Should I be closer? At least from at my end, it looked very good. How is it? How is it looks? How it sounds to me?
It's a bit quiet, but
it's. Is it a bit what?
No, it's fine.
It's fine. Okay. All right. So I'm gonna change this view for you, and then we're ready to go. All right. So, okay, guys, I'm already here. Are you ready? Okay. Simulation of a mechatronic machine, lecture number 5. Respect. Okay. So, lecture number 5. And now when you look at the original schedule, you will recognize that we are left a little bit behind. So there are, today we're supposed to discuss about generalized inertia forces, including mass matrix and quadratic velocity vector, and obviously we are not yet there. There is a few items that we need to discuss before we're ready to move on to generalized inertia forces. And I have one more example about the kinematic analysis. Remember this outstanding, really impressive stuff that happened last Monday, this extremely complicated mechanical system with one moving body. We were able to solve the kinematic response. Remember that? Yeah, I'm sure you'll never forget that because it's one of those highlights in your life. Life before and after kinematic analysis. That's how it goes. But it's not going to be only that in this course. We're going to go quite much beyond from the kinematic analysis. And that's what's going to happen today. So today we're going to discuss about forces. Remember, so far no discussion about forces or moments, because we are dealing with the kinematic analysis. And the only information you need to carry out the kinematic analysis is constraint equations and generalized coordinates. That's only the information you need. No forces whatsoever. But today we're going to step into the world of forces. We start looking like how is that we can create the equation of motion. And then, the equation of motion, roughly speaking, consists of externally applied forces, these forces that are introducing the motion to system. Point forces that may come from the different kind of actuators, hydraulic actuators, pneumatic actuators, whatever. So now today we're looking at these forces, these externally applied forces. In addition to that, there will be inertia forces. And inertia forces will be treated exactly the same way that the externally applied forces. When the externally applied forces and inertia forces are equal, we have dynamic equilibrium. And that's what we have to get in order to express the equation of motion. So today we're going to step into that world, but before that, let's look at the kinematics and one more example concerning the kinematics. And that example too, I will solve by using a MATLAB. Now there's a little bit of problems here because technical issues, because right now I'm unable to put the VPN on, and because I'm unable to put the VPN on, I'm unable to run the MATLAB in my computer. So maybe I'm going to do this example right after break. So during the break, I can put the VPN on, start the MATLAB. Once you're back from your exercises, then we can go and look at the numerical example. But I'm going to explain the equations needed to carry out the kinematic analysis within a few minutes. All right. So, summary. What we discussed last week. So we discussed last week that the kinematic analysis, first of all, it consists of 3 different levels. So we have to first solve the position level. The position level analysis is the most difficult one. It's the most difficult one because we have to deal with the set of nonlinear algebraic equations. And the method we use to solve the set of nonlinear algebraic equation was based on Newton-Raphson method, and Newton ROPS. I'm just checking because, you know, I need to tell you something, because the last time when I was streaming out, you know, my camera was frozen, and my friend from Netherlands called me, Aki, your camera is frozen. So I was, you know, checking if this is errant. It's not errant, so I'm good. So how is, by the way, my YouTube officer? Everything good? All right, good. So position level. So we use a Newton-Raphson method, and the idea of the Newton-Raphson method is, first of all, very important to understand that it's an iterative method. So you have to iterate certain number of times to get the solution. So you solve something, you solve the Newton-Raphson once is not necessary enough, but you need to keep on updating the coordinates until you reach the final destination. How you know that you reach the final destination? Well, there are many ways to define that, but roughly speaking, it's a matter of, you know, this value here. When the delta value is becoming small, you know that you reach the destination. Or they reach the predefined tolerance, like mentioned here. So once they reach that value, then you reach the final destination. You got position that you are ready to move on to next level. That will be velocity level and acceleration level. But again, you know how it goes, you know how the procedure goes. You first derive the constraint equation and compute the Jacobian matrix. Constraint equation is the difficult one because the Jacobian matrix is very mechanical. You just use a symbolic math tool. Most of them, I guess all of them, have a tool to compute Jacobian automatically. You just tell this vector respect to this vector, you get Jacobian matrix automatically. It's in symbolic form. And then you calculate the Newton difference using this equation. And now, very important to understand that you have to convert the Jacobian matrix. And the rows and columns in Jacobian matrix, they have a clear physical interpretation. Remember that? The number of rows correspond to the number of constraint equations. Number of columns correspond to the number of generalized coordinates. Generalized coordinates are the unknowns, and constraint equations is the solution to solve the unknowns. So the equation, number of equations and number of unknowns must match, and they match if Jacobian matrix is a square matrix, and it must be because you have to invert it. Now, then you get the direction how to update your generalized coordinates. So that's going to be delta q. And then you're going to just add the delta q to existing generalized coordinates. You get the new set of generalized coordinates, and with help of the new set of generalized coordinates, you update the Jacobian matrix and constraint equations. And you redo the whole thing until you reach the tolerance. That's position level. You know, by the way, I noticed, maybe you noticed that my pen is not cooperating today, so I have to use a substitute pen. So maybe it's not the clear writing today. We'll see. Okay, so here's a Jacobian. Jacobian is just a bunch of partial operations, nothing else. Don't make this overly complicated because it's not that. It's just that you do this very mechanically as it is shown here. Oh, so here. So you have a number of rows that correspond to the number of constraint equations, number of columns that correspond to generalized coordinates. That's it. Very mechanical. What are the other steps you need to take? Then once you're done with the position level analysis, you get to go to velocity level analysis, and that's going to be simply a substitution. A substitution where you have here Jacobian matrix one more time, and this is a constraint equation that are differentiated once with respect to time. Velocity level, the acceleration level, that too is a substitution problem. So you simply substitute all the information to this equation as it is shown here. And then you solve position, velocity, acceleration at a certain time. You're ready to increase the time and redo the whole thing until you reach the end of the kinematic simulation. Okay, makes sense. First in-class quiz is this. Kinematic analysis can be carried out if you know shape of the bodies. I mean, this is the only information. If you only know the shape of the bodies, can you carry out the kinematic analysis? Well, let me put this quiz, this Socrates on. Is it on already? I think that I put it on already. I did not. Oh yeah, I have a problem now because, yeah, a big problem because I need to close this this connection for a little while because otherwise you can see my password. Just a second, I will put the system back on in a second. It's not yet on, so just a second, I need to put it on. Quiz, this one, next. All right, so it's on. So and I'm back here. Now, can you check that the streaming is still all right?
Yeah.
Okay, good. Okay, so I'm asking that if you know one of the 4 items, can you carry out the kinematic, let me emphasize, kinematic analysis. Kinematic analysis. Okay, so if you know the shape of the bodies, moments imposed to system, moments imposed to system, forces imposed to system, or if you know the constraints of vector of generalized coordinates of the system, only one item is correct. And today, it will happen. You know what will happen today? 100% success rate. It will be this particular in-class quiz that you're going to score 100%. It will happen. Okay, so let me take a look. Okay, so you're not ready. So we have today, we only have, for online participants, I would like you to know that we have only a handful of students here in the class. So, but altogether seems to be 68 students. So majority of the students are following this using online, which is completely all right. Because maybe this comes as a big surprise to you guys. You get no extra benefit by sitting here. Except there's one benefit, maybe, that you can ask something from me. Online participants, they can give you a comment, so, okay, this, is no good, sucks, makes no sense, but I cannot see that. Okay? Okay, so 60, so what it is, 10 students are not yet answered, 10 students. So we'll see how he's done this. But today, next in-class quiz will be very interesting. I believe that we're going to score very high. This will be 100%, that's clear. It's clear. And the next one will be 100% too. Remember, okay, I will give you a hint. And if this hint makes you to change the answer, please go ahead and change the answer. This. All right? Okay, 2 more students. Or maybe this is double locking. You guys all ready? I want to see this because I'm feeling strong. Let's put it this way. All right, okay. 5, 4, 3, 2, 1, 100%. No. My mistake. Next, this one. Okay. Okay, remember a few minutes back I made this story about kinematic analysis. Remember when I mentioned that no force is involved? Yeah. No forces, absolutely no forces, no matter, because it's a kinematic. It's all about the constraints and generalized coordinates. So it's not about forces or moments, which tackles 2 options away. If it's not about the forces, so then, you can delete this one. So it's not about the moments, and I believe that I explicitly mentioned those words. So what about the shape of the bodies? Okay, maybe I should put color of the bodies. Can you do then the kinematic analysis? You cannot. So it's not possible. The only possibility is that you know the constraints, because it's all about the motion that is because of the constraints. And then you have to know the generalized coordinates because those are the ones you're solving when you carry out the kinematic analysis. Obviously, I still need to practice my teaching skills, but it's going to come a little later. It will. All right? So then, remember the last week we looked at the very simple mechanical structure, which was a planar structure with one moving body only. Today we're going to extend the concept to a little more complicated. Not much complicated, but a little more complicated system that consists of two moving bodies. And two moving bodies are connected together via revolute joint. So there's a revolute joint located here in a point P, and then there's a revolute joint that connects the body A to crown, and then there is a primitive joint that connects the point Q in such the way that the motion along the global y-axis is not possible. Not possible. All right? And then I'm constraining the motion along the x-axis by saying that this point Q must follow the equation, the one that is shown here. So the equation is sine 2 times time divided by 4 plus 1. So this position must follow that particular equation no matter what. Remember, the highest, kind of the biggest deal we have here is a motion. And after that comes forces. And then comes, whatever, I don't know. But, the forces, if I say that, if I say the motion must follow this equation, it will happen. It will happen no matter how much forces are resisting this motion. So this will happen. Now, what's going to be the number of degrees of freedom of our system? How many generalized coordinates I have? Two. Generalized coordinates. How many generalized coordinates I have? 6. Okay, that's correct. 6. Okay, the unclear writing is because of my finger. Then we have 2 revolute joints. So that's a total of 4. And then I have here 1 primitive joint. How much is that? 1. And then 1 driven constraint. 1. Okay. So we have 0. What that means? Kinematically driven system. No need to look at the forces because the response you can solve by using kinematics. All right, so let's make it happen then. So we have these steps to follow. So first step, form Takeoffian. Okay, what is that we need in order to make a Takeoffian? We need all the constraint equations and we need a vector of generalized coordinates. Generalized coordinates, again, is something that, tells us how is the system configuration at any given time. All right? So in a few weeks back, we learned how to make a constraint equation for a system that consists of 2 revolute joints. And at that time, the revolute joint was here, and we also look at how was the primitive joint located here. So based on that, we got 5 constraint equations that are, without further ado, listed here. So those are the 5 constraint equations that we got from the previous week. We have one additional constraint, and that's a driven constraint, the one that is imposed above position Q. That needs some extra thoughts, and we need to look how we can derive this final constraint equation. All right? So if it is imposed to point Q, what is it we can do? Well, we're going to again follow the equation that we are very much familiar with. So this one here that tells how is the position of point Q in a global coordinate system. And then once we have the point Q, then we're ready to impose the constraint. And the constraint will be imposed to global x direction, because the x direction is the one that is moving back and forth based on this guy here. All right? Makes sense? All right, so let's do it. So first what we have here is a position of body reference coordinate system, which is this one here, located here. And then I'm accounting the orientation of body reference coordinate system by 2x2 rotation matrix. And with help of vector U bar, I'm able to travel all the way to point Q. All right? So what's going to be the vector U bar? Because how the axes are located, it's going to be L divided by 2 positive direction. But divided by 2, correct, because the full length will be L. So I'm halfway done when I'm here, so I just need to travel halfway of the beam-like body. So that's going to be L divided by 2, y direction equal to 0. All right? Then I say that I have to impose this certain motion in a global x direction. Global x direction is this guy here. So I'm taking the equation from the figure and put it here. That's my constraint. Now I do the math. I will simply use again the symbolic math tool, and I will get my 6th constraint equation as it is written here. Others are again listed here in the upper right corner of the slide. So here's my constraints. So I have 6 constraint equations, 6 unknowns. 6 unknowns. Again, the unknowns are generalized coordinates. They will tell me how is the configuration of my system in any given time. All right? How is the vector of generalized coordinates in this particular case? Well, of course, it's Rx associated to first body, Ry associated to first body, angle theta associated to first body, and the very same coordinates of second body. Second body is a body B. All right, then I'll just go and do the math. I compute the Takeoff matrix. This is how it looks. It's a square matrix, 6 rows, 6 columns. All right, makes sense? Or makes sense? Okay. Then what's happened next? So that was the step is done. So now we're gonna compute the velocity. What we need in the velocity. So we have the inverted Takeoff matrix and constraints that are differentiated once with respect to time. Now here's my full list of constraints. So this is how the vector of constraints, how it looked like. So that's how it reads. Only one component here out of the 6 components that is a function of time, and that is this driven constraint. Others are not the function of time. So if I differentiate that with respect to time, I'm going to get the 0. All right? Except this guy here. When I differentiate that with respect to time, I will get 1 divided by 2 cosine 2 multiplied by time. Okay? So now I'm ready to compute my velocity based on this equation. And then the final, a little bit of painful step is that I need to go and compute the accelerations. Here, again, I need inverted Takeoffian. I need constraints that are differentiated twice with respect to time. So I need to take the result from the previous slide and differentiate that one more time with respect to time. And then I have this monster, this ugly guy that will consist of Takeoffian first multiplied by velocity, that then is differentiated with respect to generalized coordinates, and finally multiplied with respect to velocities. It's ugly. It's a monster. So it's a dirty guy. Okay, but anyway, so that's what we need to compute. And then the final one here, we have Takeoffian that is differentiated once with respect to time. Our Takeoffian is not the function of time, so this component will vanish. We can ignore it. All right, so let's make it happen. So we have here Takeoffian multiplied by velocity. It gives us a vector of 6 components. Those 6 components are listed here. And then I differentiate that with respect to generalized coordinates. I will get the matrix, 6 by 6 matrix. And then this 6 by 6 matrix is finally multiplied by velocities. Look how fast I'm here. I'm fast here because this is just a very mechanical mathematics. This is not the mathematics class, but this is beyond the mathematics. This is much more than a mathematics. Because this is all about, this love and hate and, how to live a life and this stuff. But we use mathematics to solve these problems. So that's why, I'm just speeding up when we look at the very mechanical mathematics. You go and take a symbolic math tool and you can do the same. Okay. So then finally, constraint that is differentiated twice with respect to time. This is how it reads. So then I'm ready. I have all the components. And now the simulation, I'm going to carry out that right after break, because after break I will put the MATLAB on, but it's going to take a little while to put it on right now, so I'm going to spend my break time to do it for you. Okay, what's the value of kinematic analysis? Is it really something that is needed in a real life? Well, it is needed in a real life. It's needed in a real life. By the way, do you know where it is needed in a real life? No idea. Okay, so it's needed to define, to say, the workspace of something, to see the motion of, different mechanisms, and to look at if there is a possibility of collisions. So you can make the collision analysis just to see if the systems are overlapping with another system. We have not discussed about contacts, but you can see if there is if the geometries are penetrating, so then you know that there is a collision that will take place. So you can make a preliminary studies about collisions. You can look at the workspace of manipulators, mechanical, any kind of mechanisms, robotics. That's where you can use a kinematic analysis. And then there's another example that I'm shortly explaining to you. And it is related to everyday device called bicycle. All right, this is something that is, kind of interesting because, a friend of mine, the guy that called me last Monday, he's Arden Schwab. And Arden Schwab got interested about the bicycle dynamics a while ago. And he was, very thorough in his studies. And he wanted to see, what is that makes a bicycle stable? This is a question you often hear, that, okay, what's the mechanism, or what's the theory behind that bicycle is self-stable? Self-stable means that if you take a bicycle, you push it forward, put it in a forward velocity to your bicycle, you can run with the same velocity or same speed that the bicycle. You can push it in a transverse direction. It will vibrate a little while, and it becomes stable after that. That's what happens. So what's the mechanism? What makes the bicycle to be stable? And it's, I'm sure you want to hear, okay, what it is. Is it the gyroscopic forces? Is it because of the geometry of the bicycle? The problem is that it's kind of this set of parameters that makes the bicycle to be stable. And it's hard to tell that what is that one single component that is the one that makes it stable. There is no single component. It's a combination of many things. Those equations and how the bicycle is stable, you can go and check it out. Arden's paper that was published in Science. It was published in the Science about the bicycle dynamics. Okay, so how this is related to us? Well, it's related to us because another guy, together with Arden, or partly independently, Jose Escalona from Spain, he created the multi-body model of the bicycle. The multi-body model of the bicycle, that consists of 3 degrees of freedom. Those 3 degrees of freedom are, forward velocity, lean angle, and the steering angle. And now we made a special bicycle here in a university, and we are actually measuring those 3 degrees of freedom. And we are using those 3 degrees of freedom as a driven constraint to system. And we use it in a driven constraint to figure out all the coordinates of the bicycle. So it tells you the full state of the bicycle. Measuring 3 coordinates, you can get all the coordinates of the bicycle. And that's because of the, guess what? Kinematic analysis. So it can be used in that purpose. And you can go one step ahead from that. You can even estimate the forces that are imposed to bicycle. Then you need something that you're not yet mastering the topic, but it's called inverse dynamics. Dynamics is about the forces. And we haven't discussed about the forces, but you can make an estimation like how much forces are imposed to front tire, rear tire, and other components of the bicycle. So that's where it becomes actually quite important. It's needed in many different areas, the kinematic analysis. But what is needed way much more than a kinematic analysis is a dynamic analysis. So that's what we're going to do next. So we will step into world of dynamics. Are you going to be with me? Okay? You ready? Okay, let's do it then. And remember 2 weeks back, I made that promise that things will be complicated in the future. And this is where things becoming complicated. And now, we need to look at things in a calm way and don't get nervous. I'm sure everything will be clear after we have practiced this a little while. But in the beginning, we have to use something that is called virtual displacement and virtual work. I'm sure this is not the first time you're using these concepts, is it? Have you ever heard this before? Yeah, I'm sure you have used it many times to derive the equilibrium in statics and in dynamics. We're going to follow this again, but again, of course, we're going to use our definition of kinematics, and I want you to have really understand why we're using the virtual work here, and why we're using the virtual displacement in our studies here. So let's see how it's going to be. All right. Here's a kind of like a motivation. So I have here a planar potato-shaped body, and the potato-shaped body is called body A. All right. Now the first time the force comes into play, so now there is a force. The force is actually imposed to one of the particles in the body A, and the force is imposed to this particular particle in the body A. All right. So the force is expressed by using global coordinates. This is a business as usual. So I'm sure you have seen this scenario a number of times. So you have the force that consists of x and y component along the global x coordinate axis. All right. So this force here consists of two components, x and y. Makes sense? Okay. But what is it we have in a multi-body system? Remember, in a multi-body system, we're describing all the particles, not just the one where the force is applying, but all particles using the body reference coordinate system. You still remember that? Body reference coordinate system. The body reference coordinate system is located in an arbitrary location within the body. Now, because we're using the body reference coordinate system, our kinematics is always based on this equation. All right? So how are the coordinates in this equation? Now, what are the variables that tells me how the configuration of the system? Those are generalized coordinates. So what are the generalized coordinates for this body? So those are Rx, Ry, and angle theta. These are the coordinates that we have to solve. And now you can see where the problem is actually coming, because the force is imposed using global coordinates. In global coordinates, you have two components, and I want to solve things using generalized coordinates. And the generalized coordinates are Rx, Ry, and angle theta. How many generalized coordinates we have? 3. How many components I have in a force? 2. Well, they're not matching. 2 is not matching with 3. Correct. So there's something that I have to do here. Something that I have to do to make them match. And this magic that comes into play that make the miracle, kind of miracle, converts 2 to be 3, maps this definition from global coordinate system to be expressed by using generalized coordinates. That's something that is called virtual displacement and virtual work. That's the reason we're using that. There is another reason too. We get back to that other reason too. It helps us to describe the equilibrium, but roughly speaking, this time we're using it to express the forces using the generalized coordinates, because we wanted to express the system, or we wanted to solve the generalized coordinates of the system. So if the generalized coordinates is our variables, or if they are our variables, it means that all the forces have to be expressed in terms of generalized coordinates. Correct. You cannot mismatch the coordinates. You have to decide one that you're using. You must be consistent with that. You following me? Okay. So now, how we can introduce this mapping? This mapping will be based on the mathematics, and in this mathematics, we're going to use this concept of virtual displacement. And virtual displacement is a very important component in the concept of virtual work. So let's get started from the virtual work. But even before we get started in the virtual work, let's look how is it work. how is the definition of work, and then we can learn a little bit about this mathematical mapping. But big idea is this, we have to introduce the mapping. Now, if we can do this trick, this virtual work trick for externally applied forces, then we can also do that for inertial forces. Because remember this, you have seen this equation. Oh, it sounds very unclear. Let me try to make this more clear. Okay, you have seen this equation. No, I don't need this. F equal the mass multiplied by acceleration. A here stands for acceleration. You have seen that before. Okay, so that's our basic equation. And then came a guy called D'Alembert, and he wrote the equation like this, and became super famous. Okay, so there was a little bit of more than just that, because he understood that inertial forces can be treated same way than externally applied forces. So here you go. So that's exactly what we're gonna follow today. So we're gonna first deal with this guy. And once we learn how to deal with this guy, then we're gonna do the same for inertial forces. Makes sense? Not yet time to have a break. So, okay, let's look at the virtual displacement. So virtual displacement is something that you have to consider as a mathematical tool. As soon as you start to think about, okay, virtual displacement. So how it actually looks. So how small is a virtual? Because they always call, small displacement. So how small is the small displacement? And how it look in reality? You get really confused, very, very confused. We will look at the displacement, definition of displacement, and we'll look like, how that is related to virtual displacement. But roughly speaking, the virtual displacement is, for us, is a mathematical tool to introduce this mapping from global coordinates to generalized coordinates. And then, something that is very important is that during the virtual displacement, so when the virtual displacement takes place, we are assuming that the time is not running. So we consider that the time is frozen. So time is not running. And this makes it okay. So we have to invent the time machine to make it happen? No, that's not that. So it's all coming from the mathematics. So we'll look at the mathematics in a second. All right, so, here is already mentioned, real work. Real work consists of dot product of force and displacement in the direction of force. Displacement in the direction of force. So we're going to look at the real displacement, then we're going to look how that is different with the virtual displacement. So here is mentioned that the change of time is not taken into account, assuming that the time is not running when you introduce the virtual displacement. How is my explanation so far? Are you with me? You don't need to be with me, because this is, just that if you understand all what I mentioned, you will be very, very good in a multi-body dynamics. If not, you will be very good in a multi-body dynamics. Okay? Okay, so let's look. So I have here a beam-like body, and in a beam-like body I have force that is imposed to point O. Here's a point O, and the force is expressed by using global coordinates again. So it's X and Y. So the force consists of two components. And now my assignment here is to express the force by using generalized coordinates, which is coordinates associated to body reference coordinate system. Okay, so now we're going to use this concept of virtual displacement to make that all happen. But let's look first how we can define the point. So we can define the point O using this equation, that we first traveling the origin of the body reference coordinate system with help of vector r, and then we're going to account the orientation of body reference coordinate system, and finally, with help of vector u bar, we can reach the final destination, which is a point O. And that's where the force is applied, in that particular point. Okay, now we know where the force is applied. Now if we look at the displacement, then we can actually express work, or virtual work, if you may. Let's get started from the real work. Okay, how is it work? By the definition, is a force multiplied by displacement in the direction of force. Okay, how we can express that? So it's going to be, original position of this point O minus, the final position. So this is a displacement. It's a vector in the direction of force, and if I multiply that displacement with the vector, a force vector, that's my work. Okay? Do this. Do this even if you don't understand what I'm saying. It makes me feel good. Okay? All right? Okay, so then, what if this one here is very small? Very small. Okay, this is when everything becomes kind of mathematics. So let's call, if it is very small, I call it as a delta R. So I have small displacement, delta R. Okay, so how I can express this delta R? I'm just taking my mathematical toolbox. Look how we can express that. Okay, so I can express that in such a way that I differentiate the vector R with respect to time, and I multiply the time difference. In the time, like how much time it takes to do this. And then I differentiate the vector R with respect to my generalized coordinates. So this consists of two components, delta R. Okay, remember in the virtual displacement, we are assuming that the time is not running when the displacement takes place. Meaning that in case of virtual displacement, this component will be neglected. So now I can actually, look at how is my virtual displacement, and I can, to differentiate the virtual displacement, the real displacement, I'm not going to use a delta here, but I'm going to use delta. But, is it the different? Is there a different name for this? Is it delta still? Delta. Capital delta, I use a small delta instead of capital delta. The difference between the virtual displacement and real displacement. All right. So in a capital delta, I can express that. Oh my God, this writing is very unclear. Partial R divided by partial Q multiplied by delta Q. Please cooperate now. No. I don't understand what's up with this guy. Okay, but this, this is a relationship between the delta R and delta Q. So I have here generalized coordinates and global coordinates. What's between? Mapping. Mapping that converts the expression from global coordinates to generalized coordinates. Beautiful. So here we have. So this is exactly what we were after. Remember, the original problem was the problem that the force was in a global coordinate system. We wanted to express that in a generalized coordinates. Now this is exactly what we can use to make this mapping materialize. This mapping. Are you crying? Not yet. Okay. All right. So virtual work, this one here is 0, so I can express the virtual, let me take this. So I can express the virtual work in such a way that is delta R multiplied by force. And the delta here will be expressed, exactly the same way that I just did. Well, I'm not going to write this again because it's so unclear. All right, but that's the idea behind. And this, we do this all to introduce the mapping. Okay, so now let me explain this in a little bit another way. So, and then we're going to have a break. Right after the break, there's an in-class quiz about generalized external applied forces. Generalized forces stands for the fact that, they're expressed using generalized coordinates. Okay. So the force component is a force component, and when I converted the force to be expressed by using generalized coordinates, the name will change as well. So then the name will be generalized forces. Okay. All right. So this is my virtual work. So my virtual work, and look at this. So my virtual work here is different than the real work, and I differentiate that from the real work with this symbol delta. So the virtual work. And the virtual work is a virtual displacement multiplied by force. And when the virtual displacement takes place, the time is not running, so the delta T is equal to 0. So it kind of simplifies my denotation, coordinates. So now based on that I can use a chain rule of differentiation, or just looking at the previous slide, I can express this relation. Delta R is equal than the partial R partial Q multiplied by delta Q. Now delta R, delta Q are related based on this equation. So basically this relates global coordinates and generalized coordinates. That's what happens. And what actually do this mapping is this guy here. You know, again, it's a partial operation of vector versus vector. So what's that going to be? Matrix, mapping matrix. Okay. Is it all becoming clear already? Kind of. Can you do this just, you know, to please me? Thank you. I appreciate that. I feel good. All right, so now, you know, this is, you know, the mapping. So I'm just, you know, using my notations to describe how is the mapping matrix. Look at this. So mapping matrix consists of 2 rows, 3 columns. 2 rows, because in a global coordinate system, how many coordinates we have? 2, x and y. X, y. 3 columns because of 3 generalized coordinates. Rx, Ry, angle theta. So that's what I can use to do this mapping and express the forces using generalized coordinates. Okay. So this is, you know, using this denotation that we introduced, I think it was the second week, I can express the mapping as it is shown here. So now I have here 2 by 2 identity matrix, which is the submatrix of the system. Then I have this rotation matrix that is rotated 90 degrees positive direction, and that's multiplied by vector u bar. Vector u bar is telling where the force is actually applying, where the point we're looking at is actually located at.
Is this a rotation matrix? No?
It's a rotation matrix, but it's rotated 90 degrees. So you can get it by differentiating the rotation matrix with respect to angle theta. Excuse me. So here's a summary. So we started from the concept of virtual work. And concept of virtual work, we're looking this guy very carefully. And we notice that this guy actually can tell us a relation between the delta R and delta Q. And those are the 2 coordinates we wanted to relate. And how is this relation? That relation is mentioned by this matrix here. And soon I'm going to ask in my in-class quiz that what is a physical interpretation of this matrix. So seriously, it is coming. So it's the next question. I'm asking, what's the relation, or what's the, the question goes, what's the physical interpretation of this matrix here? Do you know what's the physical interpretation? It maps 2 different coordinates. What are the 2 different coordinates that it maps? Global and awesome, generalized coordinates. So that's a physical interpretation of that matrix. It's a mapping between 2 coordinates. All right, so how that reads in reality? It looks like this. Now, this is an example, so let's get back to this original concept. Let me erase this a little bit. All right, so originally I have this mapping, and the mapping I'm then using to multiply that with the vector F, force, externally applied force, point force. All right, so my mapping is actually expressed here. So this matrix consists of 2 rows, 3 columns, and then I'm multiplying that with the vector that consists of 2 components. How the final solution look like? The final solution look like this. You know, it looked a little bit complicated, but I have here original vector F, and then I have one more component that is associated to angle theta. So that's my generalized externally applied forces. So it kind of tells you, if I have this potato-shaped body, and this is where the body reference coordinate system is located, the force, if it is applying here, I'm kind of moving the force applying in the origin of the body reference coordinate system. So that's where this part is coming from, and then because of the moment. So it's the moment arm, force multiplied by moment r, that tells me how that is applying to coordinate theta, rotational coordinate. So then I have the force expressed by using three components. Three components that are associated to what? Generalized coordinates. Beautiful, beautiful. We have to cry a little bit and then we come back. I need to go to the toilet. So you too, I'm sure you have to do the same. So let's take a, it's that much already, that late already. Then we have a 10 minutes break. Okay.